So yesterday we met the factor theorem and we were solving problems like this. This is the first of three sorts of problem that we're solving. This one looks a little bit different because we're asked to get it as a quadratic, but we're not asked to break it into individual factors. But make a start. I'm hoping the first thing you will do is realise that if x minus 3 is a factor, x equals 3 is a solution. So you're going to hopefully substitute 3 in and show that you get 0. Then it's the equating step. So having shown that this is a factor, hopefully you can see that a must be 2 and c has to be minus 5, because to get a plus 15 you need a minus 3 and a minus 5. So I then gridded that out, x minus 3 times 2x squared plus bx minus 5, and that gives me that. So I've got my original cubic equals this expression, 2x cubed minus 6x squared plus bx squared minus 3bx minus 5x plus 15. And I only need to find b, so what am I going to equate? Lily, help me out. What should I equate? You pick it. You're going to equate x squared, okay? You could have done either x or x squared, so equating x squared, and that just means working out how many we've got on each side. So I've got minus 2 here, and I've got minus 6 plus b here. Okay, so I'm not writing the x squares, I'm just saying how many I've got. I'm adding them up, and the equal sign says, right, you've got the same number on both sides, won't work otherwise. So b equals 4. Now, it's interesting to consider why they haven't then expected us to break it into two linear factors. Okay. Anyone suggest why?
Does it not go nicely?
Doesn't go nicely. Yeah, that's right. It doesn't go nicely. In fact, I mean, I haven't done this, but b squared minus 4. No, so you've definitely got two solutions, but they're probably going to be absurd solutions. So we could still work out two further roots. We already know that 3 is a root. 3 is a value that makes it equal to 0. There'll be two roots here, but they're probably not nice round numbers. So that's why they've told us to stop at that point. Happy with that, Isabel?
Yeah.
Yeah. Okay. So that was a slightly sort of different variation on the fully factorised question. Let's just do one more before we move off. It was, I think I've got a dicky dongle. Coming and going. Okay, so with this one here, standard start, but rather than being asked to factorise it, we are being asked to find the solutions, the roots. So hopefully you're going to start with the root that we already know. Well, sorry, we don't know it. We've got to show it is a root. But then you've got to find the other two. So it's just a slightly different wording, but exactly the same technique. Okay, so hopefully once you've shown that x plus 4 is a factor, x minus 4 is a solution, you were able to work out that a was 1 and c was 5, then multiplied that out, did my comparison thing, did my equating. I equated x squareds, but I could have done x's. b is minus 6, so that's minus 6. I'm asked this time to find all the solutions. So what they suddenly do is to take it from a function and turn it into an equation. But we've factorised it so far. X plus 4, x squared minus 6x plus 5. So James, are you able to factorise this down?
B minus
two minuses, isn't it?
Yeah, minus 3 and 2.
Got to make 5. So I think that's going to be 5 and 1.
Yeah.
And so my solutions, minus 4, plus 5, plus 1, the roots. And so we've just got to be light on our feet and be able to respond to slightly different questions. And I'll add it to the OneNote for an independent study question. That's a good example of something that's slightly different. Again, page 154, question 5. So what about the other two types that I spoke about? Well, here is here's an example of type 2, which I am calling missing values. Missing value questions. So here we have an example of a missing value question. So you'll note that it doesn't say show that x minus 2 is a factor. It says x minus 2 is a factor. So they're telling us this time. We're not having to show it, they're telling us. And that means we don't have to prove, we know that f of 2 will equal 0. If x minus 2 is a factor, x equals 2 is a solution, and that means that when I substitute x with 2, I'll get 0 as an answer. If you do that, you end up with an equation where k is the only missing value, and you can therefore work out the value of k. See if you can do that one for me. So the key here is understanding the difference between the wording of the previous questions that says show that, and here where it says if it is a factor, find something else. Have I made a mistake, Jodie? Have I made a mistake? Oh, good. So I'm always worried when so I substituted 2 in, and I was just left with an expression with k, and I was able to work out the value of k. And that's it. These questions are much quicker. I haven't then got to go on and do anything else. It doesn't say and then factorise, it just says what's the value of k. So page 145, question 8 and 9, two very similar examples. Okay, so with 8, you just substitute 1 in. I mean, these are really quick, aren't they? These are not problematic at all. And well done if you did 9 as well. If you didn't, add it to your independent study list, and you should have got 16 as your missing value. So you substitute, oh no, minus 16. Minus 16, there you go. So you substitute in minus 3, and you get an equation with b in it, and there we go. Okay, so we've done fully factorised questions, we've done missing value questions. The last sort then, 2 missing values. And a good example of that is found in, surprise, surprise, question 10 on the same page, page 145. So I have got, this time, 2 missing values in my polynomial, in my cubic, but I'm also told about 2 factors. Now again, I'm not being asked to factorise this, not being asked to factorise it, I'm being asked to find the values in P and Q. So, Isabel, what 2 values of x do I know will make this equal 0?
1 and minus 1.
Okay, so that's what I'm going to state to start with. And what that will give me is 2 equations. So I can substitute x is 1 into this equation, which I will do. And then I can substitute minus 1 into the equation. And that's going to give me 2 equations, both of which will have P and Q. This is a simultaneous equation problem. And simultaneous equation questions, we punch the air, because we're allowed to use calculators to solve them. However, don't be afraid to solve it manually. You'll end up with a GCSE style simultaneous equation with some p's and q's equaling something. Have a go, see if you can get somewhere with that. And then question 11 and 12 are similar. So hopefully you could see where I've got these from. And I call these GCSE simultaneous equations. So back a year ago I would have solved them using my what's changed method. Some of you might have been adding the two equations to get rid of the p's. You could rearrange one as q equals or p equals and substitute it into the other. Or you could do trial and error because these are quite nice, easy numbers. I mean, don't forget though that your calculator will solve simultaneous equations. I've written them again here. So if I remind you how to use the simultaneous equation solver on your calculator, so it's so you go to menu and equation, and we normally just go straight to polynomial because we're using it to solve quadratics, but we can also use simultaneous. How many missing values, how many unknowns? Well, it's 2. And then it gives you this sort of empty equation in the form some x's plus some y's equals something. Now in this case, we're not talking x and y, we're talking p and q, but it's the same thing. So I'm going to type in 1, 1 and 10, minus 1, 1 and 4. That's what I'm going to type in to enter those equations, because I've got 1p plus 1q equals 10, and minus p, minus p plus q equals 4, and then I get my solutions that way. Except it's not x, it's p.
Wait, does it need to be minus then?
Sorry?
Oh, no, don't worry.
So I enter the equations like that, and then solve them like that. Now, you don't have to, but bizarrely, whereas we're not allowed to use the table function to factorise, this is one of those things that is accepted. I think it's because it is so GCSE that they're saying, you wouldn't be on the course if you couldn't do it, so they're happy for you to do that. Just have a little look at 11 and 12, or carry on with 11 and 12. Again, we've finished the problem. We found p and we found q. We haven't got anything else. They don't want us to go on and factorise. That's it. End of. Right. So I've done 11 there. I just used the calculator. Well done if you're doing it manually. Nothing wrong with using the calculator. One of those things we're allowed to do. And 12, I'll let you finish that independently. I know I often do that. I often say, right, do these two, and then I stop in the middle of one. I hope you are finding time to finish that in your own time. It just means that, because we're all working at different paces, I don't want you to miss out. Now, we've actually covered everything I need to cover for the factor theorem, apart from one thing, and that is that there is a different method to do the equating part. Now, you might say, well, why bother with a different method? Because that equating bit was quite easy, and if that's the case, I hope that that's great, that's good news. But what I want to do is show you an alternative method, which actually we need to use sometimes in isolation, so not just in factor theorem questions. So it's a new technique, and it's a technique that is quite fun, although I absolutely guarantee that some of you will be pulling funny faces between now and the end of the lesson. So let's look back at one of the questions we did yesterday. If you remember this question, we ended up factorising it. We started off by saying that we showed that x plus minus 1 was a factor, and we sort of, once we'd shown that x minus 1 was a factor, we did that by substituting 1 into the function and showing we get 0. We then did the equating bit. Now, I could rewrite that statement. Don't forget, what we're doing here is we're factorising. We're saying this is equal to that multiplied by that. If this is what I'm trying to find out, I could find it out by doing this. I've divided both sides by x plus 1. And so I could find the quadratic that we found by equating, and it wasn't very hard to find by equating. I could find it with a division sum. The only thing is, we've never learnt how to do division like that. We've been asked to simplify algebraic fractions at GCSE, where you could factorise top and bottom, but that's not going to help us here because we don't know the factorisation. So instead, we have a technique. It is a technique for dividing one polynomial by another, and it's called polynomial division. Now, you know, there are some things like, I mean, I don't know, some of you are starting to drive, I know, and I don't know if you can remember when you were first sat in the car. I can, okay, so 33 years ago, I can remember sat in the car, and I was so nervous that my left foot on the clutch pedal was shaking like this. I can remember it vividly. And to start with, it seems really, really hard, and now I get in the car and driving's really, really easy. I think polynomial division is like that. You're going to look at this now and you think, oh my word, I'm never going to be able to do that. That's the equivalent of your foot shaking on the clutch pedal. I'm going to do one now, we're going to do it next lesson as well. It's going to get easier, promise me, I promise you. Okay, so the sum we're trying to do is that divided by that. So we set it out as a bus stop. We set it out as a bus stop, just like that. And in fact, I'm going to write it out again up here, so I've got plenty of space underneath. Now, do you remember how bus stop division works? I hope so. Your first question is, how many of these do I get out of that? We ask a similar question now, except we've got more than one thing here. So what we need to do is we need to sort of lift this and ask how many of those do we get out of that? And actually what we do is we ask, how many of these can I get out of that? And let me ask it in a different way. What do I need to multiply that by to make that? What do I need to multiply it by? X squared. X squared. So I firstly ask, what do I need to do to that to turn it into that? You're quite right cubing it. I should have said multiply by, we get x squared. Now do you remember with bus stop, if you say, right, you've got how many 4s in 9, you put 2, and then you work out what 2 times 4 is, 8, and you work out the remainder. Well, we're going to do the same. We're now going to say, okay, what do I get if I do that times that? And what therefore is the remainder? And to help me with this sum, I'm going to put what that times that is underneath here. Normally with bus stop, we do that bit in our head. How many 4s in 9? There are 2. 2 4s are 8, take away, so that's 1 left over. It's too hard to do in our head. So here's what I do. I say, right, x squared times x is x cubed, and x squared times minus 1 is minus x squared. And I then do top take away bottom to work out what I'm left with. So that's not minus x cubed, I'm just subtracting. So this take away this is nothing, and that's always going to be the case because we've worked out what do I need to do to that to make it into that. Got to be careful here. 6x squared minus x squared. 7x squared. Did you get the x cubed? I did x squared times x, which is x cubed, and I did x squared times minus 1, which is minus x squared. Okay. So I've asked how many of these do I fit in this, and I've got that, remainder that. So I now shift along one digit like we do with bus stop, but I've got something down here and something up here. So what I do is I bring that down, and now rather than looking up here, I'm looking here. So I ask, what do I need to multiply that by to turn it into that?
7x.
I need to multiply by 7x. I then do the multiplying thing to work out what remainder I've got. So I do this multiplied by that. 7x times x, 7x squared. 7x times minus 1, minus 7x. Top take away bottom to work out the remainder. Be careful when you're taking away.
I'm definitely confused.
Which is what I predicted, wasn't it?
So is there like, could there be questions where you wouldn't be able to work it out by equating?
Well, not of this sort, but this crops up in other places. So it's a technique we do need to learn. Believe me, I wouldn't teach it if we didn't need it. But in these sorts of questions, you can always use equating. Hopefully you've got 12x there, because you've got that, take away that, which is nothing. 5 minus minus 7 is 12. So now I move along a digit. I want to ask, how many of that can I get out of that? And this is the clever bit. If you divide a big number by a small number, that's a factor of it. So if you divide 430 by 5, you shouldn't get a remainder. If you bus stop it, there's no remainder. We're told that this is a factor of this, so I shouldn't end up with a remainder. Let's do my final question then. What do I need to multiply that by to make that? Let's do that multiplying thing then. I'm going to multiply 12 by this. 12 times x, 12x. 12 times minus 1, minus 12. Top take bottom. 0. So what I know is that this divided by this is equal to x squared plus 7x plus 12. And if I multiply both sides by x minus 1, I get that. And if you look back at that question, question 2 from yesterday, that's what we got. And we then factorised it into x plus 3, x plus 4. So what we'll do tomorrow is we'll try that again and see if it gets any easier. I promise you it will. I promise you it will.